Rec-
Good afternoon. Today we're going to share about the topic on carboxylic acid and derivative. Here are the learning outcomes. This is quite a long lecture, so please be prepared. So what are carboxylic acid? They have a carboxyl group, and it is a combination of carbonyl plus hydroxyl. And if we observe the structure of carboxylic acid, it is sp2 hybridized, right? Because it forms 3 bonds. So there are 3 times sp2 hybrid orbitals forming sigma bond with 2 oxygen atoms and the C atoms of the R group, or could be a H atom. There is one more unhybridized p orbital, okay, here, that form a pi bond with the p orbital of O atom of the C double bond O. Here, because this is C double bond O. So one of them is a sigma, the other is a pi bond. The rest are sigma. So there are 3 sp2 hybrid orbital. There are sigma bond and 1 unhybridized p orbital. There's a pi bond. The shape is trigonal planar with the carbon center. Now, the longest chain bearing the carboxyl group is the parent structure. The numbering of the carbon chain starts from the carboxyl carbon with the highest priority. All right? So when you have 2 carboxyl groups present, we use dioric acid to represent it, like ethane diorite or propane diorite. So here are some of the examples of carboxylic acid that you will see during the lecture. All right? Now, for every organic chemistry lecture, we will start with the structure, followed by the physical properties, and then the preparation and chemical properties. All right. So for physical properties, we will compare it with compounds of other homologous series. So if we compare with alkanes and alcohols of similar size of electron cloud, meaning similar MR, all right, may not be exactly the same, but they're close enough. The boiling point of carboxylic acid is higher because of hydrogen bond between the acid molecules, which require more energy to break compared to ID-ID interactions between, let's say, an alkane molecule of similar cloud size. Okay, if we compare to alcohol, the acid actually have a lower boiling point. Okay, both compounds are capable of forming intermolecular hydrogen bond. However, if you look closely at ethanoic acid molecule here, the hydrogen bond is actually stronger because the OH group in ethanoic acid is more polarized due to the presence of the electron withdrawing C double bond O group. So ethanoic acid has a higher boiling point than ethanol. Okay. So the alcohol and acid only form an average of 1 hydrogen bond per molecule. So you cannot explain the higher boiling point due to more extensive hydrogen bond, unless you're talking about diethanoic acid. But here we are comparing ethanoic acid and ethanol here. So it is something to do with the stronger hydrogen bond due to the more polarized OH group in the ethanoic acid. All right. Carboxylic acid molecule dimerize in the vapor state and in non-polar solvent to form hydrogen bond between each pair of molecules. So the 2 intermolecular H bonds are formed between the carboxyl oxygen atom of the one molecule and the hydroxyl hydrogen atom of another molecule. So the H of the OH part is forming hydrogen bond with the O of the CO double bond part. So this accounts for the observation that when you measure the MR of ethanoic acid when dissolved in benzene, it was 120 because they dimerize. But when dissolved in water, because the acid molecule form hydrogen bond with water, the MR is 60, which is a singular molecule of ethanoic acid. If we compare within the homologous series, the boiling point increases down the series. But this is not because of stronger hydrogen bond. This is because of increasing length of alkyne chain, because of electron cloud size increasing, and the electron cloud get more polarized, leading to stronger ID-ID interaction. So take note that it's not because of hydrogen bond, it's because of stronger ID-ID interactions. As for solubility, the first four members of the aliphatic acids are miscible with water because of hydrogen bond. And another reason is carboxylic acid partially dissociate because it's a weak acid now. So it will partially dissociate to form ions. And the ions form ion dipole interactions with water molecule as shown in the equation. However, if you continue to increase the length of the non-polar hydrocarbon chain, which is the hydrophobic part, the solubility actually decreases. Okay, because it becomes more and more hydrophobic. Okay, the interactions with water molecules become weaker. For example, benzoic acid, it dissolves readily in hot water, but when cool, it forms a white crystalline solid, and it's only slightly soluble in cold water. Benzoic acid is the benzene ring with the COOH group. We will talk about that in detail later. I think we share about this under introduction. Now let's move on to the preparation of the carboxylic acid. So there are two main ways to prepare it. Either you can do it via oxidation or through hydrolysis. Okay. So if you want to do it through oxidation, there are two ways. So you can actually start from alkenes. Okay. Upon oxidation by a strong oxidizing agent like acidified potassium manganate, upon heating, it will be able to fully oxidize to a carboxylic acid. Or you can start off with alcohol or aldehyde, not ketone, ketone won't. You use a strong oxidizing agent, or even something that is weaker, like potassium dichromate, will be able to oxidize it successfully. Other than that, you can also use the method hydrolysis. Okay, so you can start with RCN, okay, and then you can use HCl equals or NaOH equals followed by HCl to produce your acid. So for this one, right, if you use the alkaline, because it will form this first. So you need to add acidification to convert it back to COOH. Okay, so this is hydrolysis. Alkaline hydrolysis, you need to add acid to form the carboxylic acid. Unless you want the salt, then you just use sodium hydroxide without the acid subsequently. Now, so you can actually hydrolyze nitrile, and here is some elaboration on the reactions, the equations that represent the acidic hydrolysis as well as the alkaline hydrolysis. So you have water, H+, it will just convert. There's no need to know the mechanism. You just need to know the reagents, the reactions, equations, and conditions, and the products. All right. So the N will actually come out to form NH4+. Yeah. Okay. So just remember this lah, huh? Now, let's move on to the preparation of carboxylic acid via oxidation, starting with primary alcohol. So primary alcohol can be oxidized to carboxylic acid. Okay, it will first be oxidized to aldehyde lah, and then it will then be oxidized to carboxylic acid. Yeah. Okay, so this equation is sufficient. And as mentioned, you can also start from alkene. But for this oxidation cleavage, you cannot use potassium dichromate. This was mentioned in the topic of alkenes already, so I shall not elaborate here. All right, just know that you are going to cleave this and attach the O and OH. So this one is added to it. Just know how to write the final product will do. The mechanism is not required in the syllabus. All right. You can also, if you want to form benzoic acid, right, then you can start from methyl benzene. So this is methyl benzene. Okay. Then you can convert it to benzoic acid. So here is what happened. Okay, for this one is just having substituent. Okay, 1、2、3、4. Yeah. Doesn't matter. So this will not be affected by oxidation. Only the CH3. Now, if we compare between potassium dichromate and potassium manganate, they have oxidizing abilities, but there are different benzene side chain will react with subjected to strong oxidation. Okay, so for alkene, let's repeat this. There will be no reaction with potassium dichromate, but the potassium manganate will be able to carry out oxidative cleavage of the double bond between the carbon to form the ethanoic acid here. And this part here, okay, will just become CO2. So this part here is cut off. So this part here become the CO2. This one you put the O and OH here. So this one becomes CH3, attach the OH, double bond O. And this is this one. Okay. For alkyl benzene, as mentioned just now, you will actually be able to convert this entirely to COH, but not this part. Yeah, cannot. Yeah. You must be having, because this one is, yeah, you don't have any H here. Here, at least you have a H here. You also, so it can, because you have the H there, you can remove the H for oxidation. But here, no H for oxidation. Okay, so you can form COH and this CH3 will become the CO2 using potassium manganate. Potassium dichromate cannot oxidize alkyl benzene. For primary alcohol, it can be oxidized by both oxidizing agent. Same for secondary, just that for secondary, it will just form ketone and that's it. It will not be further oxidized. As mentioned, the topic on hydroxyl compounds and carbonyl compounds. Do refer to my earlier video for references. Tertiary, no hope. Okay. Aldehyde, yes. Ketone, no. As for the primary alcohol that is directly attached to the benzene ring, it can undergo oxidation by both the reagents. Secondary, it will form the ketone. Sorry, it will be able to form with dichromate. You will just stop at ketone. But for KMnO4, right, you can actually completely oxidize it. So this part can come up as CO2 with KMnO4. Okay, so this one is a carboxylic acid. For tertiary alcohol, no, but you still can oxidize the tertiary alcohol attached to benzene ring to acid. So this, yeah, you can just like form more CO2 lah. Yeah, same here, ketone can. Ketone can. So it's a different story when you talk about the alcohol and ketone attached to the benzene ring. Like ketone itself, aliphatic one, cannot oxidize. But if it's attached to benzene ring, that's a different story. Now let's focus on the reactions of carboxylic acid. So there are two reactive centers to consider. One is the C double bond O, which will break heterolytically during the substitution because the O is electronegative, so electrons are pulled closer to it. All right. And the other reactive group will be the OH bond, which will break heterolytically also to release the proton here. This accounts for the acidic character of the carboxyl group to allow formation of ionic salts. You will also observe similar process in both phenol and alcohol. So this is a summary of the reaction carboxylic acid undergo. So you can actually be reduced back to alcohol, okay, using lithium aluminum hydride in dry ether, or you can actually allow it to undergo reaction with metal in a redox reaction, or acid-base reaction between a carbonate or alkaline to form a carboxylic salt. That is also possible. Or just simply use NH3 aqueous in an acid-base reaction to form your carboxylic salt, but you change this to NH4 plus because of the base use. And the formation of ester is a reversible reaction, as we have learned that the yield of ester is low. The conditions is using concentrated sulfuric acid as a catalyst, and of course alcohol to react with the acid. This is a condensation reaction, or we can call that esterification as well. Condensation because during the reaction, a small molecule like water is formed. Then we have a new reaction here where you can remove the OH from the carboxyl group to form the halogen using PCl3 or PCl5 or SOCl2. Just know all of them. This is a nucleophilic substitution. All right. Now, carboxylic acid are stable to oxidation, except for methanoic acid and ethene dioic acid. Okay, just remember for these two. For methanoic acid, okay, it undergoes oxidation. We learned under carbonyl compounds that Tollens reagent, Ferlin solutions are used to oxidize your carbonyl, your aldehyde, all right? It can also oxidize your methanoic acid as well. Now, so using any of these reagents as listed here, you'll be able to oxidize the methanoic acid to carbon dioxide and water because methanoic acid, the carbon is the terminal carbon. So it will be easy to break it down, okay? Ethene dioic acid is the same thing because the carbon is the terminal, so you can also break it down as well. Just that the reagent used is only a strong OA here, all right? And CO2 is formed again, as well as water. Now, this is something that you learn in O-level about why are carboxylic acid weak because they dissociate partially. And we recap the comparison of acid strengths between those organic compounds that have OH group. So based on their Ka values, we will see that this one have the highest Ka, but you have a Cl here. So the halogen here is electronegative. So it actually withdraws electron and stabilize the anion. Then after that, the second one is the benzoic acid. Again, the benzene ring is stabilizing the negative charge, okay, by dispersing it, allowing to the resonant effects of the benzene ring due to the overlapping p orbitals, okay? Then we have ethanoic acid. Ethanoic acid is even a weaker acid compared to these two. Then we have our phenol, water, and alcohol is the worst among the least. So in general, carboxylic acid is more acidic in terms of higher Ka compared to phenol, then water, then alcohol. So the relative acidity is explained, as mentioned, the stability of the conjugate base, which is formed upon the dissociation of the acid in water. So if the conjugate base is more stable, the acid is stronger. So RCOO minus is the conjugate base. It has two equivalent resonance structure with delocalization of the negative charge over the two highly electronegative O atoms. So carboxyl group has two oxygen which are very electronegative. So when the COO minus is formed, the minus is very happy because it will be stabilized by these two O which are highly electronegative. So it allows the formation of resonance structure. So the minus can come here. Then when the minus go here, the double bond can form here. So it's kind of it stabilizes through resonance. Okay. And based on experimental data, the two CO bond was actually equal in length. This proved that this negative charge is actually equally distributed between the two oxygen atoms. It spans about the same time around here. So it means that the negative charges are moving freely between the two oxygen atoms. Now, in the phenol ion, the p orbital of the O. So the bond here is formed between the p orbital of O and the pi electron cloud of the benzene ring. So this overlapping is good. So with this good overlapping, right, it allows the negative charge of the O to delocalize in the benzene ring successfully. So this is what we call resonance stabilization by the benzene ring. Of course, compared to RCO minus on top, is not as good lah. Okay, it's not as great. Okay, or good. Which explain why the ethanol acid still have a higher Ka than the phenol. But it's good enough. Okay. The negative charge can still be delocalized over the two highly electronegative. Can be still delocalized here lah. Of course, this is better because you got two oxygen atoms. Okay. The resonance structure is more stable actually. So the dispersion of negative charge will help to stabilize the phenol ion. So this is a phenol ion. That's a recap of the concept under alcohol. So the alkoxide ion is here. All right. Now, alcohol, the electron donating alkyne group will actually not disperse it. It will intensify the negative charge because it's electron donating due to the R there. The CH3 is an electron donating group. So the charge of RO minus will remain localized because it's electron donating. The minus cannot go inside. So it will remain localized on that O, which is very electronegative. So the alkoxide ion is therefore not so stable compared to phenol and carboxylic acid. So this is the explanation. No? So what is the effect of substituent or acidity? So these are the factors that will affect the stability, like the nature of the R group. So we need to look at whether the R group, right, is an electron donating substituent or electron withdrawing one. So example of electron donating as mentioned are alkyl. They will intensify the negative charge of the carboxylic ion and hence destabilize the conjugate base and decrease acidity. The examples of electron withdrawing substituents are your halogen because they are highly electronegative. So they will actually disperse the negative charge of the carboxylic ion and therefore stabilize the conjugate base of the acid and hence increase acidity. For example, if we compare this Cl and CH3, one is an electron donating group, one is an electron withdrawing group. And make sure when you do the comparison, we are referring to similar electron cloud size, meaning we will use a similar number of carbon atoms in the organic compound. So the pKa was actually lower, which means that this is so Ka higher, which indicates stronger acid. Okay, recap on the concept in ionic equilibrium. So the Cl being electron withdrawing will disperse the negative charge and stabilize the anion to increase acidity. As for CH3 is electron donating, it will intensify the negative charge and destabilize the anion. Now, Another factor is the number of substituents. So the strength of the acid will depend on how many electron donating or electron withdrawing group next to the COOH group. If we have more electron withdrawing group, the greater the extent of negative charge dispersal. The conjugate base will be more stabilized and cause the carboxylic acid to be more acidic. If you have more electron donating group, you will intensify the negative charge to a greater extent, and the conjugate base will be destabilized and making it less acidic. So these are some of the data to make reference to, like you have only one Cl here, your pKa is 2.86, but when you have an extra Cl, the pKa drop, meaning more and more acidic. And one more Cl here, even more acidic. So the greater the number of electron donating group, sorry, this one is the greater number of electron withdrawing group here. Donating group will be the opposite lah. All right, so we will not go to that. The next factor to look at was the position of the substituent on the R group. So the position do matter. So the strength of the acid depends on where is the electron withdrawing group. Okay, so this effect is called inductive. It operates through sigma bond and is dependent on the distance, the effect of the electron withdrawing substituent, which decreases as it moves further away from the carboxyl group. The closer the electron withdrawing group, the more acidic. Let's this example here. So you have the Cl here away is only 4.52. As you bring the Cl closer, the pKa drops. And if it's just next to it, then it will be the most acidic. Now, these are just one example. If you have a compound with pKa, of course, this is a stronger acid than this. Then they say that electron withdrawing Cl is closer to the COO minus group in this compound compared to this. So how do you explain that in words? So with the electron withdrawing group closer, it will disperse the negative charge. So these are the keywords: disperse negative charge to a greater extent. So it will make that acid to be a stronger acid. So if you look at this example, which is the correct order in terms of increasing order of pKa, meaning you get less and less acidic. So of course, the most acidic one, increasing order of pKa, meaning or less and less. So most acidic one is here. Okay. Because you have 3 Cl, electron withdrawing group, and then this one is the next one. Ethanol acid is more acidic than this phenol. Then alcohol is the worst. Now, let's look at the fission of the OH bonds in terms of the salt formation. So there are some reactions to look at. One is the redox reaction with sodium. Okay. Now, there will be production or effervescence of hydrogen gas with alcohol. We have covered that under the topic on hydroxyl compounds, and as well as this in the same topic, phenol. It also reacts and is even more vigorous because phenol more reactive lah, okay, compared to alcohol. Then carboxylic acid, I think it's more like more acidic, so it will be reacting with it to a greater extent. As for carboxylic acid, it will then be explosive. So you can look at the extent of reaction. It becomes more and more reactive lah. Okay, this is just effervescence. Then when we move to phenol, it becomes vigorous. And when it comes to carboxylic acid, it will be explosive. So to show that this is the most acidic, and hence it displays the most vigorous reaction. Right? Now, for sodium hydroxide, sodium carbonate, sodium hydrogen carbonate, and ammonia, no reaction with alcohol. So the way to say it is alcohol is not acidic enough. That is appropriate. As for phenol, yes, it does react with alkaline to form salt and water, but not with the other three. Acid, yes, everything. Okay, just for your reference. Okay. Now, so given this structure, if you add sodium hydroxide, what will be formed? Okay, so this one and this one will react, but this part here is not acidic enough to react with the base. Only the phenol part and the carboxyl group part. Now, another reaction that involves the CO bond fission is the condensation. So previous one was salt formation. This one is condensation. So we can actually convert it to ester when heated under reflux with an alcohol using concentrated sulfuric acid. Okay. This is another example. For this, because they are so close to each other, so you can actually form a cyclic structure as a product. It's possible because they are quite close. So so intramolecular bond can be formed due to the proximity. Quite logical, huh? Okay, another reaction involves the fission of the CO bond is the acyl chloride formation. All right. Acyl chloride, sorry. Acyl chloride. So you can use PCl3 or even PCl5 or SOCl2. Okay, so what happens is that you have an acid, you can actually cleave away the OH. So you cleave, right? It's actually cleaving here. Okay. Now, so you cleave and form ROCl, and the other product is phosphoric acid, H3PO3. Okay. Then phosphorus acid, sorry. Then this is for acid. Alcohol also can. Yeah, but it doesn't include phenol. So you can also react this, which you learn under topic of hydroxyl compound, refer to earlier video. It will be able to react with PCl3 to form the salt, and the H3PO3 can also. PCl5 is the same, just that the byproducts is different. Instead of H3PO3, you form POCl3 and HCl. As for alcohol, you also have covered this, is POCl3 also and HCl. And only for PCl5, you will observe the formation of white fumes of HCl. All right. SOCl2, you form RCOCl, HCl, SO2 here. But only in this case that, okay, in this case, you will form, I say it's the same thing, but just that this main product is different. Yeah. So you produce SO2 and HCl. In fact, this reaction is good because the reaction with SOCl2 is convenient as the other two products are both gaseous and easily removed. So this is actually preferred. All right. Dry HCl will not work because the H2 will react with the acid instead. Okay. But none of the above reagent can be used to distinguish between acid and alcohol. None. Because they both have the same oxidation. Yeah. Similar product formula. Okay, looking at the reduction to alcohol, you can actually reduce your carboxylic acid back to primary alcohol using lithium aluminum hydride. But it will not be successful with sodium boron hydride or even hydrogen emitter. All right. So if you want to prove that something is carboxylic acid, the best way is to use sodium carbonate or sodium hydrogen carbonate. Then you will see effervescence and you test the gas using lime water by bubbling the gas through lime water, which will produce a white PPT. Now here are the derivatives of carboxylic acid. They have the acyl group, like carboxylic acid. Then you have the acyl chloride. Okay, this is a very famous organic compound because it's quite reactive. You can use it to synthesize other products quite easily. Then you have ester. Okay, ethyl benzoate is something new. All right. Okay, then you have amide, which will be covered in detail in the next topic, which will be the last one in organic chem, but that is not the last topic. We still have periodic table and electrochem before I call it a day off. Okay, from my lecture series. I will just take a break from this. Okay, so in this page, we will focus on acyl chloride. What are they? What are their physical property? What are their reactions? And that's it for this part. So acyl chloride as well as ester, they actually have lower boiling point compared to their parent carboxylic acid. That is because they do not form intermolecular hydrogen bond due to the lack of the hydrogen atom. They don't have the hydrogen atom compared to your carboxylic acid. All right, that is attached to the O atom. Because you can look at this, for example, the acyl chloride, right? Yeah, versus your carboxylic acid. Okay, so you can actually form hydrogen bond here. Okay. So the predominant intermolecular forces have to be PD-PD interactions, which are weaker than hydrogen bond. Acyl chloride of lower MR possess a strong smelling or pungent smell and is irritating to the eyes because they rapidly hydrolyze in air to form HCl. HCl is irritable to your eyes. The carboxylic acid as well. Volatile ester have a strong presence and fruity odors, but not all of them. Some ester are quite smelly also. Now, the solubility of carboxylic acid derivative are dependent on the size of the hydrocarbon chain. So if you increase the length of the non-polar hydrocarbon chain, because of the increased hydrophobic hydrocarbon chains, the solubility will decrease because the interactions between the molecules and water will decrease. The strength of interactions, will be weaker. So of course, it will be less soluble. Ester in general do not dissolve in polar solvent, but they are soluble in non-polar solvent like oil. Acyl chlorides are soluble in non-polar solvents and soluble in water. Because of this reason, they can get hydrolyzed rapidly in water. Because of that, they hydrolyze rapidly in water to form HCl and RCOH, which then continued by ionization. So the ions form interactions with the water through ions dipole interactions. All right. Now, acid derivative like carboxylic acid have the carboxyl group C double bond O, and the reactions proceed via condensation, which involve the attack of the nucleophile at the carboxyl carbon. So the nucleophile will attack it. The carbon is highly positive charge, or partial positive charge, because of the halogen that is electronegative, as well as the O, they pull the electron closer to themselves, making the carbon partial positive to a large extent, and that attract your nucleophile. All right. And also the halogen, right? The Y is a good leaving group, meaning because it's electronegative, it can pull away very easily from the molecule. So nucleophile are highly attracted to the carbon, which is highly positive charge. So looking at the various reactions of acyl chloride, we have this. So starting with here, you can undergo hydrolysis. So you can actually reverse it. So just now, you can actually use PCl3, PCl5, SOCl2 to convert OH to Cl. Okay, can. But if you want to do the reverse, that is also possible. So remember just now, we have these conditions. So we can actually break the CO bond to form the acyl chloride. Yeah, through this fission of the CO bond. Yep. Which is called nucleophilic substitution. But the reverse of it, right, you call it hydrolysis. Okay, because you are using water to break the CCl bond and form back the OH. So it's the reverse of the nucleophilic substitution. Not a reversible reaction, but they do not occur within the equilibrium. But you can, it's a reverse of that. Please make sure you know the equation they will ask. All right. And then the acyl chloride undergo alkaline hydrolysis to form your O minus Na plus, or it undergoes condensation to form ester. Other reactions are also condensation by nature. You can react with an amine. So this is an amine, okay, to form your amide. Okay, a bit like what you learn in O level, the amide linkage, amine plus carboxylic acid, a bit like that, as well as reaction with phenoxide ion. Yeah, then can form ester as well. Now, let's examine closely the reactions of hydrolysis. So acyl chloride are most reactive among the derivative because of the Cl. So the acyl chloride are hydrolyzed upon contact with water, even at room temperature. So the products will be a white film of HCl and a lot of heat release. So it means it is exothermic. Because it's normally very reactive reactions are exothermic, releasing a lot of heat in the reaction. HCl is very soluble in water. So some will remain dissolved in the solution, such that when RCOCl, the acyl chloride, reacts with water, you will form a very acidic solution due to the complete ionization of HCl. Now, the ease of hydrolysis, right, of this reaction depends on two factors. The electronic factor, which is the electron deficiency of the carbon center, and steric factor, whether they are bulky substituent group that will hinder the attack by nucleophile. You can recap the concept in nucleophilic reactions in the topic on carbonyl, in the topic on halogen, okay, where we talk about the nucleophilic substitution. All right. So for electronic factor, like, okay, we're going to compare these three compounds, these three derivatives: acyl chloride, aliphatic halogenal alkanes, and chlorobenzene. All right. So how do you explain this? How the electronic factor affect the relative ease of hydrolysis and the comparison? Okay. So the C double bond O carbon is bonded to two highly electronegative atoms, O and Cl. So that makes your carbon very high positive charge. And hence it will be susceptible to attack by your nucleophile. All right. In terms of steric factor, okay, the sp2 hybridized C double bond O carbon actually have less steric hindrance because it is trigonal planar, so it's easy for the nucleophile to attack the carbon. Okay. So in terms of the order of ease of hydrolysis, we expect it to be the highest. So when you add, let's say, silver nitrate, because the chloride is removed, right, it will quickly form a white PPT with silver to form a silver chloride PPT. The second one is RCH2Cl. Now here, right, the CCl carbon is only bonded to one highly electronegative atom. So in terms of electronic factor, you lost to this by 1, which is only the Cl. There's no O. So the positive charge of C is lower, not so positive. So it's less susceptible to attack by the nucleophile. And because it's sp3 hybridized, okay, tetrahedral, so you expect it to have more steric hindrance. It's more difficult for the nucleophile to attack. So there's only a certain orientation where the nucleophile can come in. All right, that is making the nucleophile having another time. Okay, so if you add silver nitrate, you will not see PPT immediately. But if you hit with ethanoic silver nitrate, then you should be able to observe presence of white PPT. So this is the only way you can see white PPT. So this is the evidence that the halogenate alkane is less easily hydrolyzed, all right, by the water. The last one is this one, okay, the chlorobenzene. Because there's a overlapping of the p orbital, so when the Cl bonded to the C in the benzene ring, okay, it's between the p orbital and the pi electron cloud. Okay, so CCl bond has partial double bond character. So it's no cleavage can occur here. So it's actually stabilized the bond. Okay, it makes the bond stronger because of the partial double bond character, because of the good overlapping, okay, between the orbitals and the electron cloud system. So, and because it's double bond, it's electron rich, the nucleophile cannot attack. Okay, they will repel each other. So there will be no PPT even when you use ethanoic silver nitrate. Now, let's examine more reactions. So the ethyl chloride can actually react with alcohol or phenol to form ester, as mentioned in the summary flow chart earlier. So you can have this Cl replaced with the OH. Okay, OR, sorry. This is the alcohol. So it formed the ester. And it formed HCl as the byproduct. Okay, if you compare the reaction between this and the acid, right, you'll notice that for acid it's reversible reaction, right? So this reaction is more vigorous, as in more, you need heat, but this one you just room temperature will be fine. So phenol do not react with carboxylic acid. Your phenol do not react with phenol. With phenol it cannot react. So you use ethyl chloride instead if you want to make ester. If you want to prepare phenolic ester, it's advisable to first convert the less nucleophilic phenol to a more nucleophilic phenoxide ion. For example, if you really want this to react, you must convert to this first. So this makes it a stronger nucleophile. Okay. And then it will then be able to, the phenol will then react with your ethyl chloride. Okay. Can? Okay. Okay, next. The ethyl chloride reacts with ammonia or amine, primary and secondary amine to produce amide. Your amide linkage you learn in O-level. And we'll cover this in more detail under the topic of nitrogen compound. That'll be the last topic after this, later on. Okay, so basically it's just like a substitution. Okay, just treat it like that. Don't have to know the mechanism, just know the reactants and the products that will do for A-level. Then you have, okay, this one as well. This part here. Okay. NHR, yeah, correct. Here also, maybe I NRR here. So with both primary and secondary amine, tertiary amine, no reactions with the acyl chloride. You don't have the R, don't have the H there, okay, to break to form this. Okay, and HCl fumes of HCl form, white fumes, huh? So this is the amide. Okay. Now, looking at the reactions of ester, we look at hydrolysis in particular. So it can undergo acidic hydrolysis to form back your carboxylic acid and alcohol, or alkaline to form carboxylic salt. For the ester with the benzene ring, okay, you can form back whatever you want. I mean the original, not whatever you want, the original individual carboxylic acid and the phenol or the phenol ion it came from. All right. Now, how do you make ester in the lab? This is a recap of O level. So I will just quickly go through it. Basically, you use corn sulfuric acid as a catalyst as well as a dehydrating agent to remove the water to shift equilibrium position to the right. And to further shift to the right to increase the yield of ester, you use excess reagent or use corn sulfuric acid to remove the water, or use other ways to remove the water so you can shift the equilibrium position to the right to increase the yield. Similarly, you can produce phenyl benzoate using benzoyl chloride here, benzoyl chloride here, and phenol in the presence of sodium hydroxide. This phenoxide ion. That can also be done, okay, to form your ester. But to form phenolic ester, we use ROCl, not RCOH. Yeah, cannot. It won't work, okay? Now, for ester hydrolysis, right, if we just heat with water alone, it'll be extremely slow, forget it. So you have to heat under reflux with acid or alkaline. So acidic hydrolysis, you break the ester bond, you form back this. Okay, the hydrolysis of ester is nucleophilic in nature. Okay, where the nucleophile is water. Okay, don't have to know the mechanism in A level, just know that it's a nucleophilic hydrolysis, in the nucleophilic nature. But it's not just to say acidic hydrolysis. As for alkaline or basic hydrolysis, the alkaline promote hydrolysis of ester by providing the strong nucleophile. So this is a strong nucleophile, and it will be able to break this. Okay. Give me a minute. O, RCOO minus. Oh, you form back the O minus. So this one, ROH here. Yeah. Okay. Yeah, O minus. This is the salt. Carboxylic salts. So this method is also called saponification, just for info. Now, if the hydroxyl compound form is a phenol or substituted phenol, then the phenolcyte ion, a phenolcyte salt is obtained. All right, like this one. So you can break up this and form this. So 2 moles of sodium hydroxide will be required for 1 mole of the ester. 1 mole of NaOH to hydrolyze the ester. The other mole is required to neutralize the acidic phenol. All right, so once the phenolcyte salt is formed, you need to further, form the acid, neutralize it. Form this first, OH, and then you form the So this is the first NaOH, and this is the second NaOH. Okay. Okay, this one you do at your own time. You can do at your own time of this one as well. Okay. This one is basically you just I think you'll break up this here. And you form back the straight chain. Yeah. Okay, so what are the products formed when compound J heated with sulfuric acid? Okay, so this is hydrolysis, acidic hydrolysis in fact. So you break up this one. Okay, then you form COH. You break up this one, OH. So you form this product. Okay. So this is a summary. I shall not go through it. And one more thing. The carboxylic acid, acyl chloride, ester, amide do not give positive iodoform test, not like your carbonyl or alcohol. Although they are the CH3 in the last CH3, unlike alcohol or carbonyl compounds. Okay. Appendix wise is just the mechanism. Okay, just briefly go through lah. So in carbonyl compound, a recap, the nucleophile attack the carbon center, this one go up, and then after that there will be protonation. So the lone pair electrons, okay, will attack the H plus and form the protonation. So there is a protonation after the nucleophilic attack. So this will be slow, and this will be fast. So here will be slow, here will be fast as well. So for the carboxylic acid, the mechanism is a bit different from carbonyl compounds. After the nucleophile attack the carbon center, then there will be it form back the double bond here, because instead of protonation, right, it will actually form back an X, because the X here is a good leaving group. So this can happen. Okay. In the case of carbonyl compounds, the absence of a good leaving group leads to the addition of nucleophile upon protonation. In the case of carboxylic acid, N is derivative. The presence of a potential leaving group facilitate the breaking down of the tetrahedral intermediate to regenerate the C double bond O and eliminate the small molecule, leading to substitution. So this is nucleophilic addition. As for carboxylic acid, is nucleophilic acyl substitution. Okay, so the order of reactivity towards of carboxylic acid derivative are, this is the most reactive, OH, and then OR, NH2 is the worst. So it depends on the leaving group. The better the leaving group, the higher the reactivity towards nucleophilic acyl substitution. So this is the best Lg. This is the worst Lg. Okay? And these two are the intermediate. So more reactive carboxylic acid derivative can be converted to less reactive one. But the opposite is not true. Yeah. Now this is just understanding of the preparation of ethyl ethanoate, which I will not go through. You can read at your own time. Yeah. So no need lah. You just a more experimental procedure. Okay. Then this is more detail about lithium aluminum hydride, why it has to be dry, so that there'll be no reaction between the hydride with water, which are very exothermic and run the risk of forming hydrogen, which contains the danger of explosion. Okay, and the calcium chloride have a high affinity to water, prevent water vapor to enter from atmosphere, something like that. Okay. So this is just for information to read for yourself. and some mechanism that not required for A-level. So the appendix mostly is only this part is good. The rest of it is just for information. So that's it for today. I hope you learn a lot, and remember to subscribe to my channel. Okay, thank you.